Okay, so last time we discussed how to represent complex numbers geometrically. And if you recall, we discussed that multiplying a real number with iota rotates it by 90, multiplying it further by iota rotates it further by 90, and so on. So multiplying a real number 4 times by iota uh, brings it back to where it was. So it's a rotation by 360 degrees. Now, so we learned, okay, how to represent this standard form of a complex number in a rectangular form or a standard form on the complex plane, like this is x and this is y. So this is what we discussed last time. Now there is a very convenient and a useful form to describe a complex number in that form, and that really is helpful for calculations and algebra. So, and that's called a polar form, and it's actually a polar coordinate representation of a rectangular number. So this is actually, for example, if I have a complex number like z here in the x in this Argand diagram, so this is, let's say, x and y point, I can use basic trigonometry to convert this into polar form. So consider, for example, this figure where I have a complex number z, which is x plus iota y, and basically this is a point ordered pair x and y. So if I draw a perpendicular on this point on the x-axis, I'll get this length, this side. This is actually x, and this is equal to r cos theta, where theta is the angle with the positive x-axis. This is theta. Then this distance on the y-axis from my point is equal to y, and this y is equal to r cos theta. Now I can use these two terms, x is equal to r cos theta and y is equal to r sin theta, to write my complex number, which is actually this x plus iota y. So I can write this in the complex in the polar form. For example, this can be written as, if for x I put r cos theta, and then iota will come as it is, and for y I put r sin theta, and then this can be simplified to take r common. So this is cos theta plus iota sin theta. This type of representation of a complex number is called as polar representation of the complex number. This is not yet complete. We still have to simplify this part by introducing something called the Euler formula, which I'll discuss shortly. But now the point is that initially I only know this form. I know only the standard form. So how can I go from the standard form to this polar form? This is called the polar form. This one is called the polar form. So it's easy. From the figure you can see, okay, if we are going to find, let's suppose, r, so from this figure r, which is actually the distance from this origin, which is 0, 0, to my point, which is x plus iota y. So actually this distance can be calculated easily. If I suppose this is a triangle, this is A, B, and let's say this point is C, then this is the hypotenuse of this triangle. This is, let's suppose, the base, and this is the perpendicular. So I can easily find this r and this theta by using this triangle. So from the triangle, r will be equal to, actually, hypotenuse square will be equal to perpendicular square per plus base square. And this implies that r square is equal to, let's suppose I put base first. So this is x square plus y square. So this is actually r is equal to x square plus y square. And if you recall from the previous discussion, this is actually equal to this thing. This is actually the definition of the modulus, or the magnitude of a complex number. So this is actually the length of the distance between point A and point C. So this is r. This is the formula for r. And then I can easily find theta, because I know that from this triangle, tangent theta is equal to y(x), and this implies that theta is equal to tangent inverse y divided by x. So these are actually the conversion equation. If I know my complex number in this standard form, it means I'll have it means I know x and y, and then I can use those x and y here. So I will get r, and when I use them here, I'll get theta. So this way we can go from the standard form to the polar form, and we still need to simplify this polar form a bit by using the Euler formula, which I'll describe shortly as I discussed. So next, in this polar form, what's the advantage in this polar form? The advantage is that it really simplifies the algebra. For example, now in this form, I can take the power of the complex easily. For example, I have to let's say calculate z to the power 3. This can be easily done in the polar form, as opposed to this form where I have to x plus iota y. I need to open this thing. I have to multiply this bracket 3 times. If it's 5 or 6 or 7, I have to multiply it that much time, and it will be kind of a difficult. But with the polar form, this can be done easily, especially with the introduction of the Euler formula. So the Euler formula states that e to the I theta is equal to cos of theta plus iota sine theta. We need to prove this result. If I can prove this result, that cos theta plus iota sine theta is equal to e to the I theta, then this expression, which is the polar form of this complex form, it will become e to the I theta. But first I need to show that this thing is actually equal to this, and this is not very hard to show. It's easy. If I use the Taylor expansion of this function, for example, the e to the x, the Taylor expansion of e to the x is 1 plus x plus x squared by 2 factorial plus x3 by 3 factorial plus x4 by 4 factorial, and so on. If I use this result from elementary calculus, I can derive this Euler formula. Now what I need to do is here, to derive this result, I need to put, for x, I need to put I theta. So if I put I theta here, this will become 1 plus I theta square plus I theta cube plus I theta 4, and so on. So and then we can do a little manipulation and we'll get this result. So let's see how. So I'm using this expression, the Taylor expansion of e to the x about x equals 0, and I'm just replacing x by I theta. And everywhere there is x, it will be replaced by I theta. Now I can use something from the complex analysis, because I know that I squared is equal to -1. So in this term, I have an I theta. So mean iota is squaring here. So a minus will be introduced at from this term. Similarly here, this is iota cube. So iota cube is equal to iota square into iota. This will be equal to minus iota, because iota square is equal to minus iota. Now here I have iota to the power 4, and iota to the power 4 can be written as iota square into iota square. So one iota square is -1. The other iota square is also -1. So it will bring just 1. So this iota will disappear without causing any effect. Similarly, this I to the power 5 can be written as I to the 4 into I. And now I to the 4 is equal to 1, and this is now equal to I, and so on. So here we can see that in alternate terms, we'll be having iotas, and in some terms iotas will disappear. They will either give us +1 or -1. Like in here, it is giving us +1, and in here it's giving us -1. It's giving us +1 here. So it's minus iota here, and it will be plus iota, and so on. So the point is that in this infinite series, it will become kind of a two separate infinite series. One will have iota, the other will be free from iota, and we can collect those terms. So the next step will be like, this is just a simplified version of the previous step. Like here iota square is equal to -1. So this is just a neat form of this calculation. Now in the next step, we have to collect all those terms which have iota and regroup them, and similarly regroup all those terms which are free from iota. So it will take this form. Now if you recall from the basic calculus, this thing is the Taylor expansion of cos, and this thing is the Taylor expansion of sine. So this thing is equal to, this is equal to cos theta, and this is equal to sine theta. and we got our result. This iota is here. So this is cos theta plus iota sine theta. And this is our proof. So this is the proof of the Euler formula. I'm using this for the cos, this for the sine, and that's my final result. So this is Euler formula, and this is an extremely important result. This will make life really easy for us while we are doing complex algebra in future. So let's summarize things here. If we have a complex number in this form, as we saw from this basic from the basic trigonometry, so then we can replace this e to the I theta with cos theta plus iota sine theta, and this is actually the Euler formula. So this is the final shape, and this is the complex representation. So let me quickly just write, if you know a complex number in the standard form x plus iota y, then the polar form is represented like this, where r is equal to x square plus y square under the root, and theta is equal to tangent inverse y divided by x. And this can be done very easily, just a simple algebra, just putting x and y here. For example, if I take this 2 plus 3 iota, let's take 3 plus 4 iota. For this, r will be equal to 3 square plus 4 square. So it will be 9 plus 16, 25. This will be 5. So the length of this complex number is 5, and the angle will be theta equals tangent inverse y by x. So y is 4 and x is 3, and this will give theta. So the theta will come here for this particular complex number, the r will come here, and that will be its complex representation. No, sorry, the polar representation. And this is a very powerful formula. For example, or from algebraic point of view, if we are interested to find, let's suppose, the power of this complex number, like z to the 3, it's now easy. R e to the I theta whole 3. This will become R e to the I theta, and this will be R3 e to the I 3 theta. It's very easy peasy. Let me, for example, I need to give you a little homework. For example, if you take this thing, e to the minus I theta, and tailor expand it, you should get cos theta minus iota sine theta. This is something you need to verify. It will be useful in future. It's again the Euler formula, but with this negative sign. So, and it can be verified in a similar way. So taking power of the complex number is easy. Dividing two complex numbers is now easy in this polar form, as opposed to the to working in the standard form like x plus iota y, where division was a bit lengthy, but now it will become really easy. So integer power of a complex number becomes extremely easy. Like here you can see that the nth power of the complex number will be simply z to the ne, z to the n rn, and cos n theta plus iota sine n theta. Now something nice can be done from here. If I put, let's suppose, if I have a complex number which is in this form, this is like cos theta plus iota sine theta. It means that this is such a complex number which has a radius 1, which length is 1. And if I take the nth power for this one, so I can write this in the short form, e to the I theta. And then if I take the nth power of this complex number, so this is n, e to the I theta whole n. And this implies that Zn is equal to e to the I n theta. And this can be written as, if I treat this whole as theta, so I can use this formula, like the Euler formula, e to the I theta cos theta, e to the I theta equals cos theta plus iota sine theta. I can use that result here while treating this as a whole angle. For example, like I can call it alpha. So it will become then e to the power alpha, and e to the power alpha will be cos of alpha plus iota sine alpha. But I'm calling this as alpha, so this will be equal to, if I replace alpha back by n theta, so this will be equal to cos n theta plus iota sine n theta. And this is uh, known as a de Moivre's formula. So de Moivre's formula in its is basically this thing: e to the I n theta is equal to cos n theta plus iota sine n theta. And this formula can be used to derive all of the trigonometric identities you have studied previously in your basic algebra and trigonometry courses, like sine square theta plus cos square theta equals 1, sine 2 theta equal to sine theta cos theta, and so on. All of them can be proved extremely easily by using this result from the complex analysis. So this is a powerful formula. Similarly, the other variant of this will be e to the minus I n theta, and which can be written as cos n theta plus minus sine n theta. This also another form of the de Moivre's theorem with this negative argument. By the way, this theta is called argument. This theta is called argument of the complex number. Argument arg z, arg of z. Theta is called as the argument of the complex number. So this was a quick introduction to the polar form of the complex numbers, and I have a little quiz for you. Just very simple algebraic manipulation. Like if this is z, and then you need to find the real part of this z divided by z complex conjugate. So you have to divide these two, but do this in the standard form. It can be done in the complex form or the polar form as well, but do it in the standard form to do this division first and then take the real part, and its answer will be a real number, positive or a negative number. Now this one is interesting, easy. You have to use this idea of iota square equals -1 here. So you have to regroup these powers to simplify by using this fact. Okay, iota square equals -1. I did this just a few minutes ago, and its answer is 8 iota. Just try it. Similarly, this can be done. Another division of two complex number. This is one complex number, this is other complex number. Do it in the standard form, not in the polar form. Divide these two and then take the modulus. And remember, the modulus is a positive number. So the answer will be a positive number if you get it right. Then why is this complex variable the study of complex variable so important? It's extremely important from the perspective of mathematics, because it really makes life easy in certain areas, especially if you have certain quantities which have magnitude as well as some phase. So there it can bring a lot of simplicity in mathematics. So complex variable functions are extremely important whenever we are dealing with certain quantities which have certain magnitude and phase. So where does this scenario arise? This comes in the study of waves and oscillations. Like we have wave functions, classical wave functions, sine kx minus omega t. So this is the magnitude or the amplitude of the wave, and somewhere here we have the phase information here in this. So such quantities can be mathematically easily described by using complex analysis or going to the complex plane, and then things can become extremely easy. So waves in oscillation, then we have AC circuits. In AC circuits, we have something called phasors, where we have magnitude of voltages and the phases of voltages and current in AC circuits. And doing all those calculations in the complex form can make life easy. For example, if we have this voltage, V equals V naught cos of omega t, we can write this as a real part of this complex number. The complex number will be, let's suppose, V e naught e to the I omega t. And this thing is very, very easy to multiply, divide. For example, if you are adding multiple voltages, or here in this case, if you are adding multiple waves, like the superposition of waves, then we can write this thing as the imaginary part of some complex number like phi naught e to the I kx minus omega t. This real wave can be written as the imaginary part, and the imaginary part will in return will be a real number or a real function in this case. But adding such a waves, multiplying such a waves, like in the superposition, will become extremely easy with this polar form. Similarly, in this circuit, in this discussion of circuits, if we replace our voltages and currents with these complex functions, then the algebra of these complex function is extremely easy. It's easy to differentiate these complex function e to the I theta. Its derivative and its integral are extremely simple, I e to the I theta. And while the derivatives and integrations of sines and cosines are usually confusing, you have a minus sign to remember and so on. So, and similarly, in quantum mechanics, you have a wave function psi, which is a complex thing, and some phase information is related with this, and some probabilities are related with this thing, and those probabilities they are associated with the modulus or the absolute value, and then the phase information is there. So this is the complex variable plays an extremely important role in quantum mechanics, where the Schrödinger itself has iota in it, and the solutions in general are complex. So the study of complex variable can be very handy here in quantum mechanics. Similarly, apart from these waves and oscillation and circuit analysis, differential equations can be solved by moving to complex plane. So the solutions of differential equation, this is what engineers, electrical engineers usually do. That and in physics also we do a similar kind of thing, that we move for differential equation to the complex plane, and then we solve in that plane, and then take the real and imaginary part, because in the complex plane, these are the kind of functions which can be easily handled with respect to derivatives and integration. So differential equations can be solved easily by using this complex analysis. Then the very important use and the very powerful use of this complex variable function is in complex integration. So there are certain real integrals which are really hard to solve, and this concept of the complex integration, especially the residue theorem, is very, very important to solve hard integral by using this residue theorem. So in a sense, it's an extremely important area to explore and to learn, to do calculations easily. So this is it for today, and thank you very much.